So let's look at our first digital technology, which is going to be NMOS, and this is going to be pull down logic, and we'll see why it's called pull down logic just in a moment. Now, we've already seen the inverter, which we've looked at over the past few videos. Now, the inverter is nothing other than the Boolean NOT function. So the Boolean NOT is this symbol here, and it takes a value A, which is say 0, and it'll give you out the value 1. Or it'll take the value 1 and it gives us out the value of 0. So we say that the A dash is the complement of A. Now this is a circuit here, which we've seen over the previous video, so I'm not going to talk through in any detail because we should know about this circuit. So we've got a driver here, so it's the drive transistor, which is an enhancement NMOS transistor, and we've got the load transistor, which is a depletion NMOS transistor, and the depletion transistor allowed the output high to go all the way up to the supply rail, which would say possibly be 5 volts. Let's start off by looking at the NOT gate. We know that if this input A goes high, then this transistor here is on. If this transistor is on, it means that this point here is connected down through the transistor to ground. So it means that this point here is pulled down to ground. Now, if this transistor, the input to this transistor is a low input, then it means that the transistor is off. If the transistor is off, in effect we've got an open circuit here, and this point here is sitting at a high value. So this is the symbol for it here, and this is our logic table. Now let's see what happens whenever we put another transistor down below this A, this transistor here. That would mean that this point won't be pulled down to ground, that is, there won't be a connection from here down to ground unless both this transistor here turns on and this transistor turns on. That is whenever both inputs go high, and you can see that in the table here for our Nand gate. When A goes high and B goes high, this point gets connected down to ground, so this point goes low. But if either the A or B or both of them are low, it means that there isn't a connection between here and ground. So if there isn't a connection between here and ground, this point remains high. So it means that whenever we get a 0 and a 0 in A and B, we'll get a 1, that is a high. And if we get a 0 or a 1 or a 1 or a 0, we get a high. And only when we get a 1 and a 1 does this point connect to ground and we get a low. So this here is our Nand gate. And you can see here, this is a symbol for it. And the actual Boolean algebra, we're going to have the input is A and B, and the output is going to be not A times B. Now, alternatively, we could take this transistor and instead of placing it in series here, we could place it in parallel. And if we place it in parallel, we get the NOR function. So we can see here in the NOR function, both A and B have to be low in order to get a high output. And you can see here, if the value of A is low, then this transistor is off and this transistor is off. So only when both transistors are off do we ensure that there's no path for any current down through here. So that means that this point here must remain high. But if either one of these transistors, either A or B or both of them, were to go high, then we would have a path for the current all the way down through this device or both of them, which would pull this point low, so we would get a low output. So this gives us our NOR function. So from these simple devices, this simple inverter, we're able to form a whole logic family. In this instance here is going to be pull down logic, because what we're interested in is the network down below this point here, which is going to pull this value down to ground. So let's go and we'll build up a more complicated circuit and we'll see how easy it is to put the circuits together. So why don't you pause the video and try and build this circuit here. So the output X is going to equal the naught of A or B and C, or D and E, or F and G or H. And it seems quite difficult whenever you see it written down here. It looks like it's going to be complicated. But remember that the plus sign just tells us we're going to have a parallel branch, and the dot tells us that we're going to have two in series. So why don't you go ahead and try that, and I'll give you the solution just in a minute. Your answer should look something like this. We have our load device here, which is our depletion load, and we have the output, which is the other side of this depletion load here, which is the X value. Now we know that the output is going to go low if the value of A goes high. So we can put our device here, this transistor, which is our enhancement transistor, and it's in series with this depletion load. So it means that if this point here goes high, this transistor turns on and it will pull this point low. Now the next option is there's an OR. So whenever we see the plus sign, it's the OR, and the plus sign means we go and we have another branch here. So this is the second branch, and it's been brought in by this OR sign. And in this branch we've got B and C. That is, B and C are both in series. The dot is series. So we've got B and C in series. So whenever B goes high and C goes high, this point here can go low. Now there's another option here which is a plus, and this plus option here again is the OR, so it brings in another branch. But this new branch here is going to be multiplied by, that is, we're going to be in series with, and we're going to be in series with this branch here. But this branch here is going to give us the E, so that if the E goes high, we'll have a path through D and E to the ground, so you can pull it low down through this route. But there's an OR here as well, so there's another branch here. So we take out this other branch here from this point, and then we're going to have the F in series with, so the F is going to be in series with G, which is going to be in parallel with H, and this is the G in parallel with H. So this is the circuit here that is the NMOS pull down logic that performs this Boolean function here. And you can see here, it's quite easy to read it off. We can say A is going to be in parallel with B, which is in series with C, which is going to be in parallel with D, which is in series with E, which again is going to be in parallel with F, which is in series with G, which is in parallel with H. And then we're just following the series in parallel with the plus and the minus. So you can see with a little bit of practice, you can build these circuits up quite quickly. And we have a very, very neat method of creating some complicated Boolean logic using very simple NMOS circuits. So over the next few videos, we'll go through a few more digital circuits using our NMOS pull down logic, and then we'll move on to the CMOS logic. So thank you for listening. I'll get you on the next video. Goodbye.